What I'm talking about in this lecture is something near and dear to my heart, and that is mole concept. Okay, I think this is the most misunderstood principle in chemistry when it's one of the most important. I always say it's the Rosetta Stone of all principles in chemistry, because without it, there really is no chemistry that we can do without understanding this concept. And it was born out of gases. So as we do gas laws, okay, in our course, I stop to do mole concept because as we run into the derivation of PV equals nRT, okay, that N right there is moles. And I've told you guys that that clearly represents just the number of gas molecules or gas particles. And you guys understood very quickly that if you add more gas particles to a system, there's more particles colliding with the container walls in themselves and the pressure increases. So I know you have a little bit of understanding of what this N is, and of course N is equal to the moles. But specifically, what is a mole and how is it important? And the gas laws, okay, lead us to that discussion. Now again, as I go back to this Rosetta Stone of chemistry, and that is mole concept. Now, of course, it's born out of the gas laws for me, at least when I'm thinking about it. There are two things that come out, okay, that are very important from the gases. Number one, of course, the mole concept, which all of chemistry requires to have chemistry. And I mean requires. Without this mole concept, we really can't do any type of real chemistry. So every piece of chemistry requires that we have a handle of this, and we're going to talk about that today. Also, the gas laws on another topic led us, okay, it's a similar topic but a little bit different, led us from the idea that we can now come up with the mole concept. It also led us to the idea that we could actually differentiate between atoms. So the gas laws through the mole concept, okay, so it's really not a different arrow, so I'm going to change that. Through the mole concept along the way, okay, we were able to figure out how atoms differ. Yeah, and I find it to be fascinating when you think about that for a second. We used gases that we can't see, they're colorless, and we used them and studied them and measured them, and we actually were able to see how atoms differed. So by using a colorless, see-through substance, we actually were able to differentiate different type of atoms, how they differed. Now, originally, atoms differed by their masses. Okay, now we know they differ by their proton number, which is part of their mass, but right now we're talking about atomic masses. So we were able to say how much different is, let's say, a hydrogen atom to a chlorine atom, and we found out it was a 1 to about 35.5 or 1 to 36 ratio between mass, and we were able to determined that chlorine is about 36 times more massive than hydrogen. So we were the first time able to get a glimpse of how atoms existed or how they differed amongst themselves. Again, using something, peering into what atoms look like, using something you can't see, which is gases. So gases that are colorless, we were able to get insight on atoms that we can't see. To me, that's pretty fascinating. So along the way, these two things are happening. Okay, so let's spend some time on mole concept. Okay, and the atom differ is going to present itself when we get to that point. But today is more about, for me in this lecture, getting a hold of why mole concept is important. I'm not going to get to the end, okay, of the mole concept today with this lecture. I'm just going to introduce why it's important. Okay, so let's get started. All right, let's give you a simple analogy of how we build a chemical compound. Let's say we want to build hydrochloric acid. So let's take hydrochloric acid. This is the compound we want to make in chemistry. All right, so pretend you're a chemist, you want to make HCl. Now, HCl has one hydrogen bonded to each Cl. Okay. Therefore, of course, it makes sense since there's one hydrogen atom bonded to one chlorine atom, notice two different capital letters, I must have a hydrogen plus a chlorine. Okay, and it seems to me that to build this, why don't we use something that we're familiar with in grams? So let's take 1 gram of hydrogen and 1 gram of chlorine. Okay, that should give us 2 grams of my product, if in fact it works this way. Now, you probably have guessed it does not work this way, and that's why mole concept, or the idea of a mole, is important. But let me show you, if you went down this path, why it would be wrong. So let's take a hydrogen atom. Okay, and let's draw it like little tiny red circles. Okay, now hydrogen is the lightest element that we know of, and it is a very, very small atom. So to have a gram of hydrogen, okay, you would need a lot of hydrogens to make that gram. All right, now chlorine is a larger atom. In fact, compared to hydrogen, now we know this now, it is 36 approximately, 36 times more massive. Now, I'm not drawing that to scale, but you get the idea that a lot less chlorines are needed to make a gram, okay? Whereas in hydrogen, you need a lot more hydrogen atoms to make a gram. Makes a lot of sense. Each hydrogen atom is smaller. To have the same mass of chlorine, you need a lot more of them, okay? And because chlorine is so much massive, to have the same mass of hydrogen, it needs a lot less of them. That should be intuitively clear to you. Now, we're going to react these. We have our gram of each. And you probably can see already the errors in our ways by going through grams and grams only. So you probably can see that the 3 chlorines will come together and react with 3 hydrogens to make HCl. And of course, well, don't forget, there's a lot of what? Unreacted hydrogens here. So this is probably not what we want if we're trying to make an industrial process to make hydrochloric acid. We'd have a lot of unreacted hydrogens. Now, you're right, the whole thing would be 2 grams, but do we actually have 2 grams of hydrochloric acid? No, we have hydrochloric acid and a lot. Now, if you can imagine, if we're cooking cake, okay, and we had a lot of unreacted extra flour, because we did grams and not the number of moles, which we're going to move to, imagine your cake being surrounded by uncooked flour or eggs. Okay, that would be pretty gross. So obviously, okay, this is not the best way to do business. So if you can clearly see by matching particles, and chemistry at its most important and fundamental understanding is that a hydrogen particle is going to collide with a chlorine particle and produce, okay, that red there, hydrochloric acid particle. I mean, fundamentally, chemistry is about individual molecules or particles colliding, bonding, breaking, in this case, colliding and making a reaction, okay, making a covalent bond, okay, and they're sharing electrons, and that's another lecture for another day, but they're using each other to become stable and they're bonding here. But these have to collide for that to happen. So when you think about it, 1 hydrogen atom and 1 chlorine atom will make HCl. So it's not about mass, my friends, in chemistry. It's about the number of particles, right? You should know that one of these and one of these makes one of these hydrochloric acid particles, not a gram. So we can't use gram as a ratio. We have to use the number of particles, and that is where mole comes from. Mole is a word born out of Avogadro's hypothesis, which we're not getting into today, but it's a word that we use to describe a number of things. It's a word that describes how many. Now, in lab, we can't have 1 hydrogen atom and 1 chlorine atom to make this. That's impossible. There's just too small. So we have to have had a way to make mole equal to some number that we can see, feel, and measure in the lab and agree upon to be the standard by which we compare everything else. Now, let's pretend that a mole is equal to 2. Well, let's make it 3 in this case, since I drew 3. So let's take 3 of these hydrogen atoms. That equals 1 mole. Now, a mole represents a number. We're pretending that a mole is 3 atoms. That would still be too small for us to actually measure, but we're going to do that for this illustration. So 3 things. And I put little parentheses here because a mole is just a number. Don't get locked. It has to be atoms. It could be molecules. It could be pennies. It could be chairs and people. Okay. The bottom line is a mole is just a number. Just like a dozen doesn't mean 12 eggs. It means 12. You can use anything for a dozen. Okay. Now we have a mole of hydrogen is 1 mole. Making my mole equal to 3 in this case, I have 3 hydrogen atoms. Well, I have 3 chlorine atoms. Okay? So 1 mole of hydrogen atoms and 1 mole of chlorine atoms come together. And what do they make? They make 1 mole of HCl. Look at that. Same particle, 3 particles to 3 particles, and don't get this wrong here, that's 3 particles. Once these atoms bonded, this represents 1 particle. Now I know that's 2 atoms there, but now they're just a atom connected, and now they act as 1 whole particle. So these combine to make a whole particle. Interesting enough, okay? We say that 1 mole of hydrogen, 1 mole of chlorine makes 1 mole of hydrochloric acid. I know a lot of people want to add those 2 together. So if I have, which by the way is a 1 to 1 to 1 ratio. Now careful, pay attention to what I'm going to say here. Right here in this arrow here, we have 1 mole of molecules, which is the product. Molecule, I can do this. Okay, now what if I was to ask you how many moles of atoms are here? Different answer. There are 2 moles of atoms. See? Mole is not locked into just moles or particles or atoms. Okay, it can be anything you want. So the answer differs. 1 mole of hydrogen, 1 mole of chlorine gives me 1 mole of hydrochloric acid molecules. This is what this chemical reaction says. And by using moles, I have this ratio that I need to have perfection. Look at this perfection. 3 of these, 3 of these, 3 of these. And we get rid of all of the what? The extra. And now I have something called perfect cake. Perfect, we say, stoichiometric ratio. But in 1 mole of these molecules, don't I have 2 moles of atoms? Right? This is a mole of atoms. This is a mole of atoms. So this total of moles, there's 2 moles of atoms. How do I know? There are 2, 4, 6 atoms combined. So I'm counting atoms. This would be 2 moles. Why? Because each mole equals 3 in our case. We have 6 atoms altogether. So depending how I ask that question, be very, very careful. So in any case, that is why we use moles. By using moles, party people, okay, we eliminate all the extra atoms that do not bond. And we get a nice clean, reaction where all we have is the reacted particles. Okay, so we get rid of all this riffraff, all of this extra atoms that don't do anything. Okay, I made the same mistake over here. And I'm left with exactly what I need to make this react. That is how chemistry took off. Once we had an understanding that we're matching particles, not mass, then we can start doing some chemistry and start expecting some things. For instance, if I have a mole of hydrogen, from this chemical reaction, if I want to make a mole of hydrochloric acid, how many moles of chlorine atoms do I need? Look at the ratio. It's 1 to 1. I need a mole. Now, pretend I want to make 2 moles of hydrochloric acid. Since it's a 1 to 1 to 1, how much of the hydrogen chloride do I need? Don't I need 2 of these and 2 of these? Because that's still a 1 to 1. So you can see that now that I have a reaction with the right number of particles, okay, law of conservation of mass is now satisfied. Law of conservation of mass, what are you talking about? Well, you have 3 of these atoms, 1, 2, 3, taken care of, 1, 2, 3. And then we have what? We have these atoms. 1, 2, 3. 1, 2, 3. So we have used up all the atoms. We didn't create or destroy atoms. And therefore, because of that, these ratios are fixed. And once I know these fixed ratios that represent the correct number of particles, I can use them to predict how much. If I want to make twice the number of these, don't I need twice the number of these? Yeah. And that's called stoichiometry, and we're going to get to that. But the power in working with the number of particles opens up the door to do chemistry and predict how much product we have from the reactants, or know the ratios we need to make something. Okay, the key is, though, how do we count? That's the problem that we're after. Okay, how do we count 3? How do we come to a consensus of what this number is? Okay, and that's what we're going to continue with another day. We're going to need a universal container to figure out and try to understand how we can compare atoms with the same number of particles. How do we come up with that universal number? We said it was 3 in my example. Clearly 3 is too small to work with, so we're using a large number. And it's not so much a number, it really began with a volume of gases. See, gases led us to this number because gases do something special that solids and liquids do. They're affected by pressure, temperature, and volume, so we can control for those factors. And that's the clue here. We're going to go, how do we count? How do we figure out what that number is going to be for a mole? How do we actually get a mole? If I know I want 2 moles, how do I figure out to get 2 moles? You understand that why it's important, but how do we do that? And that's the next lecture, and that's the next series of concept videos we're going to do. We're going to figure out how we actually found the number that we agreed upon, and how do we use it, okay, to count. All right, and that's what's coming up next. So that's the introduction of the mole concept. This is how it was and why it was important, and it gives you a little insight of why just grams alone doesn't give us the answer, but where number of particles does. So we're going to continue this discussion to figure out how we count it, how we come up with a number, and how do we use it to unlock chemistry, because without this concept, we couldn't use any written chemical formulas and make them mean anything. We couldn't predict products. We couldn't figure out how much of reactants were needed. Nothing gets done without this concept. So we will continue with this.